All right, I guess we're going to get started. It's me again. I'll be discussing how to guarantee storage performance in CloudStack. Maybe I'll go through some of this information up here in just a little bit more depth because it's probably more relevant for this particular presentation. So I am still Mike Tutkowski, working at Solidfire in Boulder, Colorado. Mainly doing CloudStack development, been doing that for a few years now. Been on the PMC for the Project Management Committee for CloudStack for about a year and a half. And primarily working in the storage component of CloudStack, although doing some work in the hypervisor areas as well from time to time. Let's go a little bit more in depth as to what Solidfire does, because it does play much more of a role in this particular presentation. So we develop a clustered scale-out storage technology, which is based on industry standard hardware. So it's a collection of loosely coupled storage nodes, which you start at around 4 nodes, and you can scale up to 100 nodes. So all the way up to 3.4 petabytes and about 7.5 million IOPS. So it's very granular in terms of scaling, capacity, and performance. And the main purpose of this storage area network is to guarantee performance on a volume by volume basis. So you have your shared storage infrastructure, and you have your volumes carved from that pool of storage. And the nice trick that the Solidfire SAN is capable of providing is to isolate performance to each of those volumes. So you can say, I want a volume with 100 gigabytes and maybe 200 4K IOPS to be guaranteed. Or you can have a small volume with a lot of performance or a large volume with a lot of performance. You can kind of mix and match whatever meets your needs and not be concerned about that performance being taken away by some other tenant on the system. Even another user in your particular account that's using another volume in that account. The volumes are isolated from each other in terms of performance. This is an all-flash array, but not primarily for just the raw performance that Flash provides us, but rather for the consistent latency that we can draw from such a system, so that we're able to build a very robust quality of service system on top of that hardware layer. The way that we bring the cost per gigabyte to be down to be on par with traditional disk-based systems is through a lot of inline efficiency technologies like compression, deduplication, and thin provisioning. So it's a very cost-effective solution as well. So what we'll see here, my last point, is that there's a nice robust REST-like API that I make use of in my storage plugin whenever I have to interact with the Solidfire system. And this makes it pretty much the same as for anybody else who's leveraging the API abilities of this Solidfire system. I use the same API as everybody else. And this is pretty much as we see as I walk through the slides here and see how I'm bringing kind of quality of service to the storage component in CloudStack. We're using this API along the way. All right, so it sounds like everybody in the audience was pretty familiar with CloudStack, so I won't spend a whole lot of time on this particular slide. Usually I go through what a zone, pod, and a cluster is. I guess just for the sake of completeness, a zone is essentially equivalent to a data center for most purposes. A pod is equivalent to a rack. And a cluster is where your hypervisors come into play, Xen Server, ESX, KVM, Hyper-V. They're at the cluster level where primary storage has traditionally been introduced in CloudStack. So primary storage until the 4.2 release in CloudStack was exclusively at the cluster level. And it came in the form of local storage. Maybe your hypervisor has local storage, which you could leverage in the form of what CloudStack refers to as primary storage. Or you could also use shared storage, maybe NFS or iSCSI shared storage. But that primary storage until the 4.2 release was just available to you at the cluster level. So as we can see on the kind of the far right side there, primary storage is now actually available at the zone level as well. So you can actually have a shared storage system and make that storage available to hosts that are in different clusters, which is actually what the Solidfire storage plugin makes use of. And then above that, we kind of see secondary storage represented at the zone level, which this is for your ISOs, your templates, your backups, where I guess I should point out, just for the sake of completeness again, that primary storage is typically for your root disks and your data disks. So a lot of high change content, usually a need for more IOPS than secondary storage. All right, let's walk through the traditional provisioning of primary storage in CloudStack. And I guess to define the term traditional here, I'm actually referring to what CloudStack offered prior to the 4.2 release. So 4.2 has been out for maybe 2 years now. And until the 4.2 release, we only had the ability to use cluster scoped primary storage, and it was a very manual process to set this up. So the way it typically worked was an admin would go off to some kind of a storage system. In this case, I'm going to use the Solidfire system as an example. So he would go off to the Solidfire system, maybe use its GUI or its API to create a volume. In the case of Solidfire, maybe give it a size, give it a performance, guaranteed level of performance, put it in an account, and make that volume available to be accessed through iSCSI. Then, in the next bullet point, he would go over to the hypervisor side of things and create, if this is Zen server, he would create a storage repository that consumed that iSCSI volume. If it was ESX, it would be a data store that consumed that iSCSI target. But the idea here is we're putting a clustered file system on that iSCSI volume, and we're doing this from the hypervisor side of things. And all of this work is actually being done sort of manually by the admin before he even gets over to CloudStack. So there's this go over to your storage system, then go over to your hypervisor system, then finally come into CloudStack and create your primary storage. So it's a very static process, kind of manually intensive. And once you've gotten that primary storage consumed in CloudStack, once you've consumed your storage repository or your data store, you've brought that into CloudStack as primary storage, you're finally able to make use of that primary storage through disk offerings and compute offerings. And it sounds again like everybody was pretty experienced with CloudStack, so I won't go into too much depth on this, but a compute offering is basically your template for your virtual machine. It specifies how much virtual CPU resources you want to give to the VM, what kind of memory, where you want your root or your boot disk to reside. And then your disk offering would basically be your template for additional data disks. How large do you want that data disk to be? In this case, what kind of performance characteristics do you want associated with that data disk? So you'd make these compute offerings and disk offerings, and then you'd spin them up to finally leverage that primary storage that you kind of painstakingly went through these steps to set up in the first place. What we're going to go to in a bit is now what's available as of the 4.2 release in the form of completely automated provisioning, and then the ability to actually offer quality of service on a volume-by-volume basis within CloudStack. So you can have virtual machines that have a root disk which has its own guaranteed level of performance. That same virtual machine or different virtual machines can have their own root disks and data disks, each with their own performance characteristics, shielded from other users on the SAN so that they don't impact the performance of your volumes. And this is all done in a very automated fashion. So just to kind of compare and contrast in another image here, what we see on the left-hand side is what I sort of described as the traditional approach. You have some pool of storage. That's that traditional storage RAID group, kind of the gray box. And then on top of that, you would carve out your volume on either your, like an iSCSI volume or an NFS share. And then that would be given to CloudStack as primary storage. And then on top of that, on that iSCSI volume or NFS share, that's where you can run a lot of virtual disks. So you have a lot of root disks, a lot of data disks. They're sharing that back-end resource. So even if your back-end resource did have a guaranteed level of performance, the virtual disks that are running on that back-end resource, they're kind of like mini tenants that compete for the performance that's available to that volume. So it's really hard to guarantee to a virtual disk in this kind of an environment a certain amount of performance. To get around that, we have what's on the right-hand side and kind of what the rest of this presentation entails. And this is a model where every virtual disk actually has its own back-end volume. So the back-end volume has its own performance characteristics. There's only a single virtual disk on that back-end volume. Therefore, that virtual disk has those performance characteristics. And then you can depend upon those performance characteristics even though that virtual disk is housed on a storage system that is sharing storage amongst a lot of tenants in your cloud. So kind of the right-hand side is where we're looking to take, well, actually where I have taken things with the Solidfire storage plugin. And I don't actually, I guess, want to completely de-emphasize the left-hand side because there are currently restrictions within hypervisors in terms of how many back-end volumes a hypervisor can support in a given cluster, for example. So right now what ends up happening is a lot of times people will kind of mix and match these approaches where they do need guaranteed performance to a particular root disk or data disk. They'll use the right-hand side approach, just a single back-end volume for that virtual disk. In other environments where perhaps they want performant root disks and data disks, but they don't necessarily need to guarantee that performance, we can still make use of that approach in the bottom left. So ideally, as we move forward and hypervisors are able to relax those restrictions in terms of how many back-end volumes they can support in a cluster, we'd be able to move more and more to that right-hand side approach where every virtual disk has its own back-end volume. All right, so let's walk through the process of creating primary storage in CloudStack that's, in this case, based on the Solidfire storage plugin and makes use of this new approach. So the first thing we'd notice is at the top, there's a scope field, and this is actually going to be set at the zone level now instead of at the cluster level. So this is one of the bigger differences here. This is going to be primary storage that's available to potentially all of the clusters within your zone. And we'll see in detail what that exactly means as I walk through the slides, but just kind of know right now that this is zone-wide primary storage. The hypervisor, instead of being targeted at a particular hypervisor type, we're going to select any for the hypervisor. Right now, this is really supported for Zen Server, ESX, and KVM, but select any, and pretty much most of the commonly used hypervisors in CloudStack are supported. And again, we'll see actually in detail what this means, but when you do actually dynamically create volumes and give them to a particular hypervisor type, that volume, once it's given to Zen Server, for example, needs to continue to be used in that Zen Server environment. It could be a data disk, which is detached from a VM in one cluster and reattached to a VM in another cluster. As long as the hypervisor is still Zen Server, we're fine there. And the same rules apply for, say, ESX. You could make a data disk and attach it to a VM in one ESX cluster, write some data to it, decide later that you want to port that data to a VM in another cluster. You can then detach the data disk from the VM in the first cluster and reattach it to a VM in another cluster. The only, so to speak, catch there is it has to be the same hypervisor type. But any is kind of at a high level right now, that's what we'll select. Provide the zone that you'd like this primary storage to be part of. Give it a name as you're used to. And then the protocol field is actually something that was newly introduced in the 4.5 release for the GUI. This is actually more of a GUI concept. This plugin has been supported since 4.2, but the GUI was augmented in 4.5 to make it easy to create primary storage that's based on custom plugins. And one of the sort of new protocols there is this so-called custom protocol. And all that means is there's going to be a new field below, which is called provider. That's your plugin options. This is a list of storage plugins that CloudStack, when it started up and did an inventory of storage plugins, these are the plugins that the management server located. And it's made easily available in a drop-down, so you can go and select. In this case, I've picked the Solidfire storage plugin, and you can to see all the different plugins that are available in your environment. And if they're available for use at the zone level, then you could select those as well. In my case, the Solidfire storage plugin is what we call managed storage. It doesn't require you to go off and manually manage your volumes, manually manage your storage repositories or your data stores, like I walked through in the first couple slides. Managed storage means that it will handle that for you. So when the time comes to spin up a virtual machine that needs a root disk, managed storage, if it's invoked to do this task, will go off to the back-end system, make the volume with the right size, the right performance characteristics, hand that over to CloudStack. CloudStack understands that this is managed storage. It will go to your hypervisor, let's say that's Zen server. It will create a storage repository for you, which consumes that newly created volume, and then it'll make that available to your root disk or your data disk or whichever situation you're in there. So that's what managed means, that this particular type of storage will actually be handled. A lot of the previously sort of manual tasks will be handled by CloudStack. The capacity bytes, which is kind of a sort of a amusing field because it's not in gigabytes. It's just it's always been in bytes in this GUI dialogue. Anyways, that's actually 2 petabytes that I'm providing access to from the Solidfire system. So usually I just kind of go into a calculator and come up with 1 or 2 petabytes and then just copy paste it so I don't make any mistakes. But what we're saying here, and to kind of distinguish this from other types of primary storage, this is not a 2 terabyte volume. This is just saying that you can use up to 2 petabytes. This is not a 2 petabyte volume. You can use up to 2 petabytes of storage from the Solidfire system to create volumes. So you may make many, many volumes until you hit that 2 petabyte limit. The other limit we're providing to CloudStack here is right below that, the capacity IOPS. So we're saying here that you can use 4.5 million IOPS from the Solidfire system. So you can dynamically create volumes, root disks, data disks, until you hit that capacity bytes limit or you hit the capacity IOPS limit. So these are some of the things that we'll check in the plugin to make sure that you don't go over those limits. So the big point to note there is that it's not pre-allocated volumes we're dealing with. This is just information to the plugin to say, when someone needs a new virtual disk and I need to create a back-end volume to support that virtual disk, I'm going to take that space and that performance out of these numbers. And if I can't do that because there's not enough left, then I'll fail that operation. The URL field is very vendor specific. It's just a collection of key value pairs that provides extra information to the plugin in question. Yeah. Did you guys have questions? Yeah. Yes, in fact, I actually do not have 2 petabytes on my lab system or 4.5 million IOPS. This is completely oversubscribed in this example. Yeah.
Okay, no, but I mean, if you allocate from a customer perspective that they have, 1 terabyte chunks that you give them with guaranteed IOPS.
Yes.
Is it based on the actual usage, or the minute that equals 2.5 petabytes, then you're done, even though there's an ample amount of space left?
Yeah. So what I do right now is, if you ask for 10 gigabytes, I subtract 10 gigabytes from this number, even though on the Solidfire system, everything is completely thinly provisioned. When you create a 10 gigabyte volume, almost no space is taken up. So it's pretty much from a user standpoint, these numbers, not necessarily at all what because the Solidfire system is, especially if you're using it in a cloud where you have multiple templates that are almost identical, most of that stuff is deduped, not to mention it's been compressed, and then these volumes are all thinly provisioned. So this is all, these numbers are from really like an end user point of view.
Okay.
Mm-hmm.
When you create a machine and it provisions storage for that, or creates that volume, how does it handle snapshots? If you
It's
50 gigs and it makes 50 gigs, how is it?
Yeah, that's a great question, and I wonder if it's possible to wait till the last couple slides, and then if you have questions after that, let's go into depth on that. I do handle both hypervisor snapshots and then what CloudStack calls volume snapshots, backups. I have a technique to handle that as well. So once I cover that, let's go back and see if you have any further questions on that. But that's a good question too. All right, so yeah, the key value pairs are basically collection of information like what's the management IP address, what's the storage IP address. So typically our systems, they're going to run on a 1 gig network for management, a 10 gig network for storage. All of the activities like creating volumes, putting them in an access control list, putting them in the appropriate account, that's all being done over the management network as you'd expect. And I guess one of the questions I get, we'll kind of go on a little bit of a Solidfire aside here, is in a loosely coupled system like ours, what is this IP address referring to? So we call this a virtual IP address because it actually has the ability to float across nodes in the cluster. So you could picture maybe your cluster is 20 storage nodes. Each of these storage nodes is an independent computer, basically, with memory and CPU, and it's got a bunch of SSDs. And they're loosely coupled with each other. They each have their own IP addresses, and then there's one floating IP address for the management for the control plane, and that's what we're referring to as the management virtual IP address. So your commands are sent to that IP address, and let's say that particular node goes offline, maybe for maintenance, or you've rebooted it after installing a new version of the operating system. As soon as that IP address is no longer supported by that node that's been rebooted or gone offline, another node will pick up on that IP address and service those management commands for you. And it's very much the same idea from the data plane point of view. There's a storage virtual IP address. So you would log into the volume, do an iSCSI login. You'd go to whoever is housing that storage virtual IP address, perform your login. If that's successful, it will rebalance you to one of the nodes in the cluster. So we'll get a nice distribution of iSCSI connections across the cluster. If one of the nodes goes offline, it's housing a bunch of iSCSI connections. Those will basically be reestablished when the host that lost the connection realizes that it's lost a connection, goes back to the storage virtual IP address to re-log in, is successful at that, and then will be rebalanced to one of the surviving nodes in the cluster. So it's a very robust system. I won't go into the other key value pairs. They're things like username and password, credentials basically, so that you can submit your commands to create volumes and take snapshots and all sorts of management activities like that. And then the last one is the storage tag field. This works exactly, if you're familiar with storage tags in CloudStack, this is the same thing. This is just a way to describe your primary storage so that when the time comes to execute a compute offering or a disk offering, that compute or disk offering has a list of storage tags, and those are basically requirements. The storage that you put this data disk on or this root disk, that storage has to support this list of storage tags. It could be something very specific, like this data disk has to be placed on primary storage that describes itself as Solidfire _1. Or it could be really generic, could be something like fast. If the primary storage describes itself as fast, it's a candidate for housing this particular root disk or data disk. So in this case, I'm keeping it pretty simple. I'm just saying that the primary storage I'm creating here, it just describes itself as Solidfire 1. And we'll see in a bit when I make, I believe it's a data disk offering, in the storage tags field, I'm just going to specify Solidfire_1, and that's kind of how it ties in to know to use this particular primary storage. But you could get a lot more complex if you'd like. So were there any questions on this stuff so far? Feel free to ask questions along the way. So once we've created our primary storage, just as you'd expect, you can go to the infrastructure area, look at primary storage. It shows up just like any other primary storage. It is a little bit different, as I've kind of noted, in two areas. Number one, it's zone-wide, not cluster-wide storage. And number two, it's not in reference to a pre-allocated volume on some back-end system or an NFS share that was pre-allocated. This, as we saw, was just set up with reference to a Solidfire system, telling me how many bytes I can use from it and how much performance. So in that case, it's very flexible. Other than that, it's going to look pretty much just like any other primary storage would to you in CloudStack. And I guess one question I do get sometimes is, once you start spinning up virtual machines whose root disks make use of this primary storage, do you see multiple entries for primary storage? And the answer is no. It's just this one primary storage. You could be housing 10,000 volumes off of it, and you're just going to see this one primary storage entry. What you would see is the amount of available capacity and performance would be reduced by the sum total of the volumes that you have active. All right, cool. So let's go in now and actually make use of this primary storage. And the way we would do this is just like for any other primary storage. We could, in this case, I'm going to give an example using a disk offering. And what we'll do here is we'll go over to the, I believe it's the Services tab. You can't actually see it in this kind of cut-off screenshot, but in the way bottom left in the CloudStack GUI, there's the Services tab. We'll click on that, and then we can see kind of in the middle there's a Select Offering. I went ahead and I picked Disk Offering, and now I'm in this screen. In the upper right, this is our area to click on a button to allow us to create a new disk offering. And so I've kind of circled that as sort of being indicative of the fact that I've clicked on that button. And now we'll move over to the next screen here and kind of see what would pop up. Now, in reality, you're really only getting one dialog popping up. This is just showing two separate versions of this dialog, and I'll kind of explain in a minute what the differences are. Pretty much everything that's not highlighted here is just business as usual for any disk offering. Give it a name, a description. You do want this to be specified as shared storage. Some of these fields do not apply in our case, in the case of Solidfire. Provisioning type as thin. Doesn't matter what you put there, the Solidfire storage driver will ignore that setting since everything is going to be thinly provisioned on this particular storage system. The area that is of interest, and maybe I should point out, above that circled area, that's where I'm specifying the size, just like you would for any other disk offering. In this case, I've specified 100 gigabytes. Let me see here. Yeah, okay, so right above the disk size in gigabytes, there's a custom disk size checkbox. I'm not sure if everybody's familiar with that, but if you check the box, what that gives you the ability as an administrator to do is to actually pass that size option on to your end user. A lot of times in public clouds, that's not really something that many administrators choose to do, but in a lot of private clouds, that is it's kind of like a solution that some choose to kind of implement. So if you check the box, the disk size in gigabytes row will disappear. And then when the time comes to actually make a volume based on this disk offering, the end user will be able to put in the size of the volume. Now, in a similar kind of spirit, with performance, we have the same option. If we look in that circled area, and now I'm kind of on the left-hand side, we see QoS type, so the quality of service type. By default, this field is empty, which is kind of, I guess, backward compatible with anything prior to quality of service in CloudStack, quality of service from a storage standpoint. If you drop the combo box down, there's actually a couple options. There's Hypervisor QoS, which is really rate limiting for the KVM hypervisor. That's the only kind of quality of service that's supported in CloudStack right now from a hypervisor's point of view. Then there's a storage option. So that's what I've selected here. And by selecting that storage quality of service option, I'm presented with a few fields below. There's the custom IOPS, which is a checkbox, just like that custom disk size. There is the custom IOPS, where, I just said that. There's min IOPS and there's max IOPS. You can typically, as an administrator, what will happen is the administrator will usually put in the minimum and the maximum IOPS. Now, if you know your end users and their familiarity with setting performance characteristics like this, you could check the custom IOPS checkbox and do pretty much the same thing you did with custom disk size. You can pass that, in this case, that performance option onto your end user. And you can actually do this in any combination. You can pass the capacity and the performance options onto the end user, one or the other, or neither. So it's very flexible in that sense as well. So here, on the left-hand side, I've chosen to not check that checkbox, which is the default. And then I've put in 1,000 minimum IOPS and 2,000 maximum IOPS. Now, what that means is actually going to be dependent on how the storage system is implemented. In my case, that is a 4K I/O size. So if you know your average I/O is maybe 64 kilobytes or something like that, you can actually go, we have a nice slider in our GUI, which is something I've considered implementing in CloudStack, but it allows you to kind of translate, well, what's 1,000 4K I/O mean if my I/O is 64 kilobytes? You can kind of do that translation in the Solidfire GUI right now, and then come up with a number in terms of 4K I/O that makes sense for your 64K I/O or whatever. Which is also one reason, too, that it typically makes sense more for administrators to fill out the minimum and the maximum IOPS, because that's sort of arcane knowledge there. You have to kind of really know something about the system to understand what those numbers mean. And most users don't need to know what the back-end storage system is, let alone understand that that particular number that somebody's asking me for is in terms of 4K I/O. So usually an administrator will fill in the minimum and the maximum IOPS. But you do have that option to do custom IOPS as well. Now, the area right below that circle called Hypervisor Snapshot Reserve, we're going to return to that at the end when we talk about snapshots. What that really entails, though, maybe I'll give you a little sneak peek. Typically, when we have this kind of plugin being used, you're going to have a single virtual disk per backend Solidfire volume. That's great. Now, what happens with snapshots? If they're hypervisor snapshots, you have those Delta files, and they typically reside in the same storage repository, or if it's VMware, the same data store. The hypervisor snapshot reserve allows you to specify kind of like a percentage that you want to make the backend volume larger than the virtual disk so that you can accommodate those Delta snapshots if you plan on using those. So as an example here, if it's a 100 gigabyte virtual disk, I'm saying 100, I should have maybe used a different number, but it's saying 100% hypervisor snapshot reserve. That means take your 100 gigabyte virtual disk and add 100% of that to arrive at the size of your backend volume, which would then be 200 gigabytes. And then you'll have your virtual disk on that, and you can then put on additional Delta snapshots as you take hypervisor snapshots. Now, that's one approach to snapshotting. There's also the approach of actually taking snapshots on the backend system. And I think that might have also been where your question was going, and we'll cover both of those toward the end. But that kind of gives you a little bit of a sneak peek into how hypervisor snapshots are supported. Otherwise, if you said, I wanted a 100 gigabyte virtual disk, and you went and you made a 100 gigabyte Solidfire volume, you, depending on how the hypervisor does thin or full provisioning, it might not have enough space to put that 100 gigabyte virtual disk inside, you have to have a storage repository, which takes up some space for its metadata. It's basically a clustered file system. Then you have the virtual disk within that. So this allows you to make that backend volume larger than the virtual disk itself and sufficient to accommodate the metadata for the SR as well as delta snapshots for hypervisor snapshots. And the good part about this is you can make that backend Solidfire volume pretty large. If you can make it, it doesn't really matter from a Solidfire standpoint. It's not going to really take up a whole lot more space. The only thing you are taking up is that number, that capacity IOPS that we talked about. So if you say you have 2.2 petabytes from the SAN that you want to use at most, and you make a 100 gigabyte virtual disk with 100% hypervisor snapshot reserve, that's 200 gigabytes that's going to be subtracted from that capacity IOPS. More just sort of like number manipulation, but on the back end for the Solidfire system, you are taking up very little space, whether it's 100 gigabytes or 200 gigabytes, it doesn't really matter. Okay, cool. So moving along here, we've made our disk offering. Now, let's say my job as an admin essentially is done at this point. All I had to do was make sure I had a Solidfire system available. The Solidfire plugin comes standard with any version of CloudStack 4.2 or later, which actually, as of the 4.2 version of CloudStack, that was when CloudStack first started supporting storage plugins to begin with. So there really was no access to vendor features prior to the 4.2 release. If you were iSCSI storage prior to 4.2, you just integrated into CloudStack as iSCSI storage. There was no making use of your snapshots or customizing your quality of service or doing anything like that. You were just kind of plain vanilla iSCSI storage. So as of 4.2, that's when the storage framework was revamped and kind of enhanced a lot to support not only zone-wide primary storage, but also plugins for CloudStack in the form or for the storage component. So if you have CloudStack 4.2 or later, you have this plugin. So in this case, you don't actually have to interact directly with the Solidfire system to create volumes ahead of time. You don't have to go to your hypervisor to consume those volumes that you created because you never created those volumes. All you have to do is go to kind of like one-stop shopping, go into CloudStack, go create primary storage, do it the way we just described, and you're ready to go. Make your disk offering, and then you're essentially done as an administrator. Now I've logged in as a regular user. I've gone over to the storage tab, and in this case, I already have a virtual machine up and running. Maybe I've decided, I don't know, it's running SQL Server or something. It needs a couple data disks, maybe one for logs, one for data. And so I'm going to actually go and make a supplemental data disk. And in this case, it's very important to me that that data disk have not only the capacity I specified, of course, but a certain guaranteed level of performance. And so this is when I come into the storage tab. I go to the upper right, I click Add, so I'm going to be adding a new volume here. And then it's the same kind of idea. We're going to see two dialogues here, but it's really just one dialogue in reality, and there's a couple of variations that I want to touch on. So here we are. We've got our dialogue. In the kind of the left-hand side there, we'll start there. We do what we do for any other data disk in CloudStack. We give it a name. We provide the availability zone that we want that volume to live in, and then we pick the disk offering. In the left-hand side, I've picked a disk offering where the administrator specified not only the capacity, but the performance. So there's nothing left for me to do as a user. If I'm happy with that size and that performance, then I can just hit the OK button, and I'm fine. In the right-hand side is where the administrator has given me a little bit more freedom to choose. So in this case, I've picked a disk offering where the administrator has selected the size for me, so that's not customizable, but he's left me with the option to select the minimum and the maximum IOPS. And again, just kind of point this out again, the administrator can do all four permutations. Maybe give you both size and performance, give you neither, give you one or the other. So it's very flexible. So either way here, whether the administrator gave me one option or any of those four, I select what I want, I fill in options if they're available to me, and I hit the OK button. Just like any normal CloudStack virtual disk, we see this. Actually, there's not a list in this particular screenshot, but this would show up in our normal list of volumes. And at this time, nothing has actually happened. Typically with CloudStack virtual disks, when you create one, it really just equates to a new entry in the volumes table that's in the cloud database. There's no real interaction with any hypervisor at this point in time because you haven't actually attached that disk to a VM, so we don't really know what the hypervisor type would be anyways. So all of the real entertaining stuff happens when you first come and attach that disk to a virtual machine. Then we know what the hypervisor is. And actually, CloudStack will run through its orchestration logic at that point as well. It'll look at your disk offering. It'll analyze the storage tags. In this case, my storage tag was very easy. It just said Solidfire SAN1. It will take that requirement. It will go through, It will go through my primary storage list, looking for primary storage that can satisfy that requirement. I just had one primary storage in this case, so it was pretty straightforward. Zone-wide primary storage, it described itself as Solidfire 1 or something like that, Solidfire SAN1, I can't remember what it was, and it'll pick that primary storage. At that point, it starts invoking functionality on whatever plugin supports that primary storage. In this case, it's the Solidfire Storage plugin. It'll say things like, go off and create me a volume. What that means to my plugin is take the information that you provided in that disk offering, along with how you configured me for the SAN, what the management virtual IP address is, what the credentials are, go off and create a volume. And in the Solidfire situation, it's a multi-tenant system by design, just like CloudStack. So we have the concept of accounts. You have volumes that live within accounts. Just like in CloudStack, how your accounts own resources. It's the same idea. So for every CloudStack account that initiates an action like spin up a virtual machine, and it picks this particular plugin to provide the primary storage, whatever account that CloudStack user is in, the plugin will make sure that an equivalent account exists on the Solidfire system. If it doesn't, it'll make it. It'll then make the volume, assuming we have the appropriate capacity and performance remaining. Once it has that in place, it'll provide an IQN to CloudStack, which can then go off, and based on your hypervisor type, it can go to Zen server, create a storage repository, consume that volume, go to ESX, make a data store, consume that volume. If it's KVM, it's a little bit different. It's actually a little bit simpler in a sense because there's no clustered file system involved. It'll just give the iSCSI information to the KVM host, which will log into the iSCSI target directly and pass that basically pass that device into the VM as its own virtual disk. So there's a lot of orchestration logic that first happens when you attach that disk to the VM. And let's actually see what this looks like as we kind of walk through here. So we've selected our virtual machine for this data disk. We hit the OK button. All right, so what happens on the Solidfire system? At this point, the plugin has been notified it needs to make a new volume. It goes off to the Solidfire system. If it needs to, it makes that account. Then it makes a volume. And so what we can see in the bottom left here is that the volume is created. Now remember, this volume was not in existence prior to this request from the user. So this is a newly created volume. When the user is done with this data disk and deletes it, this volume will be deleted, and that space will be relinquished to be reused by some other data disk or root disk. So this volume has been created. We can see in the far right, and this is kind of actually looking at it through the Solidfire GUI. So just to be clear here, there's no need that you would actually have to go in and look at this way. This is just sort of for demonstration purposes to show what's actually happening. If you were to go in through the Solidfire GUI after you've created this data disk and attached it to a VM, you would see a new Solidfire volume. On the far right, we see the performance characteristics. we see 1,000 minimum IOPS, 2,000 maximum, and in this case, 3,000 burst. And I don't think I really touched on burst. So minimum is pretty much what you would expect. Minimum is a guaranteed performance level. If, even if a component in the system fails, if an SSD fails, if an entire node of SSDs fail, as long as you did not over-provision the performance of the system, we can meet those performance guarantees for each volume. The maximum is what you can expect to achieve if the system has that available performance and you're pushing the system hard enough. So you'll usually be somewhere between minimum and maximum. Now, let's say you have kind of like a bursty workload, which is pretty common. You're going along, a database needs to perform a checkpoint or some other kind of I/O-intensive activity. There's a lot of cases where systems that only, well, for one, minimum is kind of, minimum is a unique feature of the Solidfire system. Maximum is very much like rate limiting. But rate limiting by itself is very kind of coarse-grained quality of service. What burst allows you to do is actually, in certain situations, if you haven't been using up all of your maximum performance, you accrue credits, and then if you need to, you can actually burst above your maximum for some extended amount of time, finish your I/O-intensive operation, and then you either come back kind of your own free will, or if you decide not to come back, the system will reel you back in to be equal to or below your maximum. So kind of think of minimum, that's your guaranteed performance. Maximum is like rate limiting, but with burst, it makes it more flexible. Makes it more, not so, I guess, so much of like a sledgehammer approach. If you really have the performance available and somebody needs to go above their maximum for a little bit, this allows that to happen. And right now, a minimum and maximum are directly supported in CloudStack. I calculate burst based on a parameter that you set when you set up primary storage. All right, so on Xen Server, I've kind of alluded to this, but what happens on Xen Server is that once that Solidfire volume has been created, we automatically, well, we pass that information back to CloudStack. So for one, the Solidfire plugin doesn't know anything about Xen Server or ESX or KVM. It knows how to make volumes do stuff on the Solidfire system. Once it's done that and provided a volume that can be referenced through an IQN and through the storage virtual IP address, that information is then available to CloudStack, which understands that this type of storage is managed. That means that CloudStack needs to send the appropriate command to whatever hypervisor you're using. If it's Xen Server like here, we can see in the bottom left, Xen Server receives a command from CloudStack to create a new storage repository, making use of that volume, that iSCSI target that was just newly created. Once that has been created, a virtual disk image, which will be the size of the disk that you requested in the disk offering, will be created within that storage repository. And most of the time, you'll just see the one virtual disk image within the storage repository. Unless you're doing things like taking hypervisor snapshots, then you would see multiple virtual disk images, but they're all cumulatively representative of the same disk. So either way, the performance is guaranteed for that disk. If this were ESX, we would actually see a data store instead of a storage repository, but it's very much the same concept. That data store has a clustered file system on it, and instead of the VHD file for Xen Server, you'd see a VMDK file for ESX. Very similar, though, in both regards, actually. KVM, which is the next slide, is where it gets a little bit different. In this case, what actually happens is KVM is given the iSCSI qualified name, the IQN, the IP address on the data path to log into the iSCSI target. So that's your storage virtual IP address. And it goes ahead and does that, just like ESX or Xen Server would do, but it doesn't really touch that device at that point. It doesn't lay down a clustered file system or anything like that. It just kind of keeps that disk in a raw fashion and then makes it available to the virtual machine that it was instructed to make it available to. So either way, you have, from the virtual machine's point of view, a new virtual disk which has the appropriate size and then, of course, the appropriate performance characteristics. So yeah, so right now it's supported Zen Server, ESX, and KVM. And I think this kind of covers this first part, and I think this is where we get into the snapshot part. Oh, I'm a little bit ahead of myself. No, this is actually something I should point out before I get into snapshots. This is what it actually looks like in the CloudStack GUI. Just to kind of make this clear, I guess, these volumes, even though they were dynamically created and everything was done dynamically like that, they show up just like any other CloudStack volume would show up. And actually what I've done here is I've gone back, and I'm not going to illustrate this like graphically, but I've gone back and I've rerun that disk offering. Let's say I've rerun it 3 times, and I've made 3 volumes, and I've attached each volume to a different VM, and each VM was running on a different hypervisor type. So one Zen Server ESX, one KVM. And so what this is illustrating in the circled portion is that I've taken that one primary storage at the zone level, and I've taken space and performance from it and created 3 volumes, which are actually being used by 3 different VMs in 3 different hypervisor cluster types. So what we can see here is in the circled portion under hypervisor, we actually see VMware, Zen Server, and KVM. So that's kind of a unique area as well. Is not only is it zone-wide primary storage, but it's zone-wide primary storage that can be used for different hypervisor types as well. So that's pretty cool. All right, now I get to the snapshot part. So really there's 2 different kinds of snapshots that people are usually interested in. Hypervisor snapshots and what CloudStack calls volume snapshots, which are really more like backups. From CloudStack's point of view, a volume snapshot, they call it a snapshot, but you're really taking that data and copying it to another storage system. And in my mind, that's really more of a backup than a snapshot. A snapshot is typically something that you can quickly restore your system to. It maybe records the data at a certain point in time, but it doesn't take that data and move it to a different system. It's just on the same storage system, and maybe you can revert your volume to that state if you want to. Maybe for testing purposes, you get to a nice golden image, you take a snapshot, you run some tests, analyze your results, and then you decide you want to roll the volume back to that point in time. That's when you use a snapshot. Backup, oftentimes, that's used for disaster recovery. But in CloudStack, backups are typically called volume snapshots. So what I'll be referring to here are both hypervisor snapshots and volume snapshots. So hypervisor snapshots are basically what we discussed a while ago. You have, if this is Zen Server, you have your storage repository, your virtual disk is within that storage repository, and you're making changes to it as you go along. You're writing new blocks to it, you're writing new blocks to it, and you decide you want to keep that state. So you say to your hypervisor, take a snapshot of that particular virtual disk. So what ends up happening there, it's implemented a little bit differently with Zen Server and ESX, but the basic idea is that your virtual disk image is essentially frozen at that point in time, and you get a new virtual disk image that collects the new writes. So that way you kind of have these layers. You have multiple virtual disk images, and a lot of times what will happen is a read will come into the newest one. If that particular block doesn't exist there, it'll go to the next, I guess, child in the chain and look for that block. And so that's how we maintain delta information and know if you were to revert that current virtual disk to a previous state, we know where you were at that point in time. So the idea here is that those virtual disk images would typically be contained in the same storage repository if it's Zen Server, or the same data store if it's ESX. And we needed a mechanism to essentially make the backend volume large enough, not just for your virtual disk, but potentially for these delta files as well. And that's where that hypervisor snapshot reserve field comes into play. And I kind of, I guess, described most of the relevant portions of what that field does. I guess the takeaway there is that it allows you to kind of configure how large you want the backend volume to be to account for potential hypervisor snapshots. So you have that flexibility. Were there any questions about that part before I got into volume snapshots? All right, so typically volume snapshots, what I like to call backups. In CloudStack, what you do there is you say, on a volume by volume basis, you say, take to your Solidfire volume, then that will diverge from the snapshot, thus taking up additional space on the system. But almost all of that is deduped to begin with. So when you take that snapshot, you are in an identical state. And then going forward, your volume can diverge. But if it doesn't diverge too much, most all of that space is exactly the same between your snapshot and your volume. And you can just keep on doing that. You can keep on taking snapshots. So it's extremely fast, extremely space efficient, and people obviously want to take advantage of that. And so this is one of the areas that I've been working in the 4.6 release, and then I'll be continuing to work on this in the 4.7 release. It depends how much we want to go into depth on this, but it's actually not a super easy solution because of an issue in Zen Server. So right now, if you are using Zen Server and you have your storage repository consuming your Solidfire volume, you have your virtual disk image on that storage repository. Now let's say somebody says, I want to take a snapshot, not a hypervisor snapshot, I want to take a storage snapshot of that virtual disk. Well, that virtual disk is on a backend volume along with the storage repository, which is fine. We can take a snapshot instantaneously on the Solidfire system. The problem comes in actually making use of it in CloudStack, because Zen Server has this concept of immutable unique identifiers. It has an immutable UUID for the storage repository. It has an immutable UUID for every virtual disk image. And if you try to mount that snapshot at the same time that you have your other volume up, you now have a storage repository that there's two storage repositories that have the exact same UUID. And there's two VDIs with the same UUID. Now this is a problem that ESX recognized a long time ago. I mean, this has nothing to do with Solidfire. This has nothing to do with storage systems in general. They're doing what they need to do with taking snapshots. The problem is the hypervisor needs to be more flexible and understand that if you're trying to mount another storage repository with the same UUID, it could be because of an issue like what you're doing here. And so ESX provides a mechanism where you can actually, when you mount it, you can actually say, yes, I want you to, I know it's a duplicate, I want you to resignature it and basically give it a new UUID. And all of the virtual disks within it, give them new unique identifiers. And so what I'm working on for ESX will be actually very efficient and just very, very fast. You'll be able to take the back-end snapshots essentially instantaneously, and we can resignature them, make use of them for creating templates, for creating volumes. Zen Server right now, we're working with people at Citrix in that community to have a similar feature implemented in Zen Server where we can actually either resignature the UUID or do something like that, where we can actually make use of these back-end snapshots really efficiently. Otherwise, what you're left with is it's better than the traditional backups that CloudStack has, but it's not nearly as good as what I have in ESX. What I have to do right now is if somebody says, take a snapshot of this particular virtual disk, if it's on Zen server, what I have to do is make a brand new Solidfire volume, give it to Zen server, tell it to make a brand new storage repository, and then tell Zen server, copy that VDI from the source SR to the destination SR, which is very similar to what happens with NFS. It's going to be much faster, and everything's going to be deduplicated on a Solidfire system, but you still have that front-end CPU cycles that are being consumed, as well as the network bandwidth. So ultimately, it's not the solution that I'd like to go with. I'd like to have something more like what ESX allows with resignaturing those clustered file systems in the virtual disks. So anyways, that kind of gives you a feel for some of the work that I'm doing in 4.6 and 4.7, especially in 4.7. 4.6, hopefully within the next month, we'll have that released. And that has a version of this snapshotting, which is doing that front-end copy on Zen server. Hopefully in 4.7 or some release thereafter, I'll be able to replace it with something like what I can do with ESX. And that'll be a very efficient, very fast snapshot. It won't require any front-end CPU, won't require additional network bandwidth, and then you'll have all of the benefits that you expect with your normal backups, being able to create volumes and templates from them in CloudStack. So did that answer your snapshot question? Okay, great. And I think that's actually, actually I just talked about this, but I didn't switch the slide over. So I think we can pretty much just ignore this. I just talked about it. And I believe that's the end of my deck. So does anybody have any questions? All right. Oh, question.
A bit of a mean question.
Yeah.
Why don't you have a small system that was like a smaller version of this so that you could use it per fault?
A smaller version of Solidfire?
Yeah.
That I can use for what?
Well, currently you're proposing it as zone-wide primary storage.
Yes.
But wouldn't it be possible to create a scaled-down version of the system and have it per fault?
Per pod, yes. In fact, you can actually take the same Solidfire system if you want to, and you can add it into CloudStack as multiple primary storages. So in that way, you could kind of control your capacity and your performance in a more fine-grained fashion. So there's a bunch of areas that I kind of have on my to-do list. So I have kind of workarounds for what you're saying on a pod-by-pod basis, but there are definitely other areas that I'd like to address that more fully. Yeah. Yeah. Anybody else?
For the volume burst feature, that's similar to the EBS one.
You know, I'm not familiar with how that works on, you said for EBS, for elastic block storage? I'm not exactly familiar with how that works. So what I can tell you is the way ours works is that the minimum, that's a guaranteed number. So as long as you're pushing the system hard enough, you'll get that number. You can typically push it all the way up to maximum as long as there are resources on the SAN to support that. If you do not push it up to maximum, you're accruing credits. And then when the time comes, if you want to burst above that maximum, that's when we start expending those credits and allowing you to burst above maximum, again, as long as we have the performance available to support that bursting. And you can basically burst until you're done with your operation and kind of choose to go back down below maximum. Or if you actually just expend your credits, at that point we'll pull you down into your maximum again. Credits are accumulated over time, yes. All the time, I believe so. Now, there are very detailed specifications as to how that works, and I'm not exactly privy to all of that knowledge, although I'm sure it can be made available if that's something people are interested in. But the basics would be that if you are not using your maximum, you do accrue credits, and those credits can then be expended at some point in the future, up to either expending them all, or there's a certain time limit, I think, as well. And then we might pull you back in as well. Like I say, there are details around that, but the gist is it makes it more flexible than just being rate limited. So typically, that's one of the things too you have to kind of think about when you hear quality of service. That's going to be a very popular term in storage in the coming years. You have to kind of understand what that means. In this case, we're talking about quality of service in a very fine-grained level of detail. In other cases, you can be talking about prioritization schemes. So you could say, well, maybe I have a high, medium, and a low pool, and I'm going to put this application in the high pool, like a lot of IOPS versus sort of like, this is the third time I've done that. I'm just going to have to step away from the microphone. Geez, so prioritization schemes, you could kind of think of that as like threading priorities. One guy is a little bit more important than the other guy. That doesn't actually tell you anything about what kind of performance to expect, other than that you're at priority level 17 or something like that. You're more important than the guys below you, but not as important as the guys above you. In a cloud environment, you don't really have any insight into what that means. I mean, you can, if somebody says, I can pick levels 1 through 10, well, I don't know, maybe I could have great performance with level 2. Maybe I'm paying more for 5 and not getting anything more out of that. You don't really know what your neighbors are using from the system. Are they all level 6s? Are they all 7s? You don't really know. So prioritization schemes in a cloud environment are not very effective. They are only effective if you are an administrator who has detailed knowledge of the workloads that are running on your storage. In those environments, you can get away with it. In this case, you would not be able to really get away with that. So that's one thing that people will call quality of service, and it does have its place. If you know your workloads, then you could get away with that. Other ones that are typical are rate limiting. So that's just saying, I'm not going to tell you anything about your minimum level of performance. All I'm going to tell you is your maximum. I'm going to protect the system from people using up too much resources, but I'm not going to tell you anything about what you can get. And in this case, what we're doing is we're taking that much farther, where we're saying, not only do you have maximum and burst, but we're also telling you, you will get this level of performance. And in fact, you will get that level of performance even in fault conditions. So if you lose an SSD, or if you lose a node of SSDs, as long as you have an oversubscribed performance on the system, you have access to those resources. So it's a very fascinating system from many points of view, but that in particular. So yeah, any other questions? All right, thanks.